Recording. Okay. Jump right into it. Well, first off, we're going to do difference in two means today. So now we've moved on from one sample mean, which we had on the test, which yes, I have not finished marking. In fact, I haven't even started. I don't know why I said finished. I haven't even had a chance to start. And so they're sitting there and I'll get to them. So we did one sample means, and then we said, okay, what if I have two samples, but a special case of two samples where I can pair them across the observations? Then we have paired data or matched pairs. And then today, we're going to talk about the difference in two means, meaning I have two independent samples, two independent sample means, right? And so usually I focus on the independent samples. But before we do that, I had promised to send out an announcement on Moodle, and I did not do that because I forgot. And so, hey, this is shaping up to be just me confessing to stuff. But it's trivia night, so this, I'm pretty sure it's tonight. Let's see here. Is it tonight? Can someone confirm? Yeah? Okay. So it's tonight. And it's in the trades atrium. So doors open at 7. $5 includes pizza. Pretty good deal. And there's a prize, or it seemed like prizes for the most festive outfit. So go have fun. That's what the end of term is all about. It feels like it's all cramming, but it's also about having fun. Okie dokie. So is it too late if I send out the announcement after class? I feel like it's a little late. Tonight, I'll still do it if I remember. Okay, let's see here. So in terms of introducing the concepts, what I want to do is focus on the formula sheet. So now we're moving through our formula sheet. We looked at paired data. You can text each other. We looked at paired data. And then, so now we're moving into two sample means. Now, what I want to highlight here, without actually highlighting, is that here we analyze the mean difference. So we calculate the differences, and then we talked about the mean difference and how it compares to 0, right? Whereas for two sample means, we're analyzing the difference of two means. So now I've got two groups, no way to match them up. And what does that do? Well, it creates a mess in terms of all our variables, right? Because when I look at, well, I can look at the behavior, the theoretical behavior, but we usually ignore that, or I do. And then we can look at the confidence interval for mu1 minus mu2, the difference in the population means, okay? Now, my point estimate is my best guess at what that looks like, right? The sample of mean, or the mean of sample 1 minus the mean of sample 2, right? That's my best guess at what this looks like. And then the standard error has to take things into account, like the standard deviations from each sample, the sample size of each sample. Kind of fun is that the sample sizes don't have to be the same. So that's neat. Yeah. So what I'm going to do is just bring in this whole kit and caboodle. And what you've probably noticed is on one of the assignments, or I posted an ANOVA bonus assignment, and then the two samples, there are some two independent sample mean questions on there. So, right, so for two independent samples, we're gonna have X1 bar and X2 bar, right? We're gonna have sample means from each group. We're gonna have S1 and S2. We're gonna have sample standard deviations from each group, right? We're gonna have N1 and N2, sample sizes of each group. Yeah. So there's a lot more components to introduce. So in terms of recognizing the sentence structure, right? If you have two means and two standard deviations and two sample sizes, then usually that's a sign that you have two independent sample means, right? And so here I'll say N1 and N2 can be different, which to me is kind of cool. And usually they are different. Sometimes they're the same, and that's allowed. In terms of let's focus on our confidence interval, right? So once we have all that information, it's really just a matter of plugging values in and then just making sure that your interpretation about the confidence interval is going to be about the difference in the means, right? Because that's what you're building your interval around. Yeah. T star, you find it the exact same way as before. And I know what you're thinking, but Emily, then I need my degrees of freedom. Please stay on the line. Way down here, our degrees of freedom, spoiler alert, I guess, is going to be the smaller sample size minus 1. So you just look at the smaller sample size minus 1. Technically, it's quite a bit larger than that, the calculation, but this gives us a conservative estimate, which we use, and that's fine. Most of the time, it's actually all of the time, it'll be fine. Okay. So the minimum of N1 minus 1 or N2 minus 1 is how it reads. But when you see this, you're just going to think, oh, my smaller sample size minus 1. That's my degrees of freedom. Yeah. And so that's nothing we can't handle. Right, T star, once you have your degrees of freedom, you can find that line on your T-table. Same thing, if you're choosing between lines, you go for the smaller one, because otherwise you assume that you have more degrees of freedom than you actually do, right? And if you're using software, it'll do the huge calculation for you. Okay. S1 squared, well, that's the standard deviation of group 1 squared over N1. Make sure you do these separately and then add them up, right? If you try to punch them all into your calculator, unless you're really good about brackets, then it'll make a real mess, right? You don't want to be doing something weird like adding this in the denominator or something like that. So just make sure you take your time. But besides that, it's nothing crazy. Look at how good we are at confidence intervals and hypothesis testing, right? All you need for a confidence interval, right? Your question would be, okay, what's my point estimate? My point estimate is X1 bar minus X2 bar. That's my best guess at what this thing looks like, right? So how far we've come, this is your point estimate, making this square root the standard error of the point estimate. What's really nice about means is the standard error is the same in a confidence interval as it is in a hypothesis test. Whereas for proportions, it changes depending on if you're doing a confidence interval, we use p hat. And if you're doing a hypothesis test, you use p naught. So then you have to keep track of those, right? But for means, this chunk is the same as this chunk, right? So here, these are the same. Once you've calculated it once, you don't have to do that again, right? You can just jump to the value. And so if you wanted to do both, right? Usually I only make you do one of the two on an exam, right? But just in case. So then that saves us a little bit of work. Our hypothesis is going to have the same structure as when we were comparing two proportions, right? So if I want to know how mu1 compares to mu2, the first thing I have to do is assume that they're the same, right? Until I have proof otherwise to say, oh no, mu1 is less than mu2, right? That kind of thing. And so two potential setups for our null hypothesis, mu1 is equal to mu2, or equivalently, mu1 minus mu2 is equal to 0. It's just a matter of what you prefer. But notice, right, if mu1 is equal to mu2, then mu1 minus mu2 is 0, right? You can move it around. And so I don't even bother writing it on the formula sheet, I guess. Lazy. But technically, it's minus the hypothesized parameters, which is minus mu1 minus mu2, but our hypothesis is always that it's 0, so that's why it's not on there, right? So really what our test statistic is doing is it's figuring out how far this difference is, so the sample differences that I saw, how far is it from 0, taking into account the standard error, which is just the spread. All right. And with that, I reckon we're ready. Oh yeah, trivia night. Any questions before we do an example? All right. So, talking about diamonds. Oh, there's a lot on here. I'll read it to you. Weights of diamonds are measured in carats. Fine. 1 carat, we're going to call 100 points. Okay. And 0.99 carats, we're going to call 99 points, etc. Right? And the reason for that, maybe it's always true, but the reason for that in our analyses is we need to be able to put the carats on some comparable scale. And so then we can talk about the cost per point, right? And then we can analyze the mean difference in point prices, right? And so some facts. The difference between the size of a 0.99 carat diamond and a 1 carat diamond is undetectable to, I feel like the naked is a little bit excessive, but to the human eye. But does the price of a 1 carat diamond tend to be higher than the price of a 0.99 carat diamond? Missing a carat there. We can test this. What would this look like in terms of our alternative hypothesis test, right? This sentence structure tells me that, well, okay, I guess I could start with my null hypothesis. Why did I want to skip it? Because it's so boring, right? Mu1 is equal to mu2, or mu1 minus mu2 is equal to 0. I'm going to use question-specific subscripts just to keep them straight, especially in my hypothesis. So I'm going to have mu of 1 carat is equal to mu of 0.99 is my null hypothesis in this case. The reason I'm highlighting this is because we're going to make it a little bit easier on ourselves and make it a two-sided test. Okay. But I want you to see both of them, because you could solve this once you've got the tools. And honestly, you can already solve this, right? We're setting up our null and alternative hypotheses, which you've got a pretty good understanding of, right? Just from the question, because what would that look like? How does mu1 compare to mu 0.99? 1 carat diamond tend to be higher. Oh, close for business. Once you have your null and alternative hypotheses, right? Even if you don't know what to do, your next step is to calculate the test statistic or do the test. Going to the formula sheet, okay, that's going to be whatever follows my null and alternate or my null hypothesis on here. Oh, yikes, looks like I have to calculate a huge T. But then when I have a T, I know how to use the T table to find the P value. And then when I have the P value, I know how to make the conclusion, right? If the P is small enough, I have enough evidence to reject H naught. And there, we can all go home. Done. Nah, we'll do it, right? But you have all those tools, so you can answer this. But for us, we are going to test, so because that can be confusing, right? So it introduces the scenario, the more likely scenario that we would be interested in. But then to simplify things, we're going to test to see if there's a difference between these average point prices. So that means that H naught has to be the same, right? We always have to assume that the two things are equal until we have proof otherwise, 0.99. But if we want to know if there's a difference, then mu1 is not equal to mu 0.99. The only change that happens between these two is in step 3 for our p-value, right? Here in the second version, I have a two-sided p-value, whereas in the first version, I have a one-sided p-value, right? Sometimes the difference between those two p-values can kind of make or break and change your conclusion, but usually it doesn't. So like I said, in order to be able to compare equivalent units, we're going to divide the price of 0.99 carat diamonds by 99 and 1 carat diamonds by 100 and compare the average point prices. Cute diamond. Actually, I mean, on the screen, it's a huge diamond. If we made a side-by-side box plot of the data, which we do, this gut reaction, what's your gut reaction? Well, it looks like the 1 carat diamonds, these are the prices, the point prices. Let's emphasize that. So these are the point prices. Tend to be just generally higher for the 1 carat diamonds, right? And generally lower, although there's quite a bit of overlap. So that's what we want to determine. Are these significantly different? Okay. If you're looking at two box plots and they're all overlapping, what does that mean in terms of your null and alternative or your hypothesis test rather? Means you're probably not going to have enough evidence to reject H naught because they're basically the same, right? And so here, this gives me reason to say, okay, I'm going to do a t-test, throwing that terminology out there, right? Just whenever you calculate a t, you call it a t-test. And that's really common language just in the workforce and things like that. And so I'm going to start slipping that in there. But when I look at this, I say, okay, looks like there might be a difference here. So let's go and confirm. We need a slew of information. Each sample is going to have a mean, a standard deviation, and a sample size. So the most convenient way to communicate that tends to be in a table, right? And I'll give you practice in the practice for the final. I'll give you practice reading where the information is in the blurb, right? But it makes for quite a long blurb, but also in a table, right? So that you've seen both. So we find that the mean of a 0.99 carat diamond is 44.5, which is less than 53.43, right? We want to know if it's significantly different, I guess. But then we could make the extension later, which we technically shouldn't do, but it's called fishing, but we're gonna do it anyways. Then we've got the standard deviations and your sample sizes. As long as you assign one of these things to group 1 and the other things to group 2 and stay consistent, it doesn't matter which one you're calling group 1 and group 2, right? And so here, let's call this group 1 and let's call this group 2. Order doesn't matter as long as we are consistent. Oh, thank you. I sensed it. I should have checked in with you. Okay. So from our formula sheet, we already know that the parameter of interest is mu1 minus mu2. So in this case, if I let the 99 group be group 1 and the 100 be group 2, then my parameter of interest, which is the thing I want to learn about, is going to be mu of 99 minus the mu of 100. More relevant to us in our calculations is the point estimate, right? So that's going to be the sample mean of 99 minus the sample mean of 100. And we want to pick the correct set of hypotheses. Well, we already did this. See, we could have rattled through. I was joking when I said we were done after talking about the formula sheet, but also that's it. We're done. But let's just go ahead and first thing I do is look for any options that don't have an equal sign in the null hypothesis, because I always have to have an equal sign in the null hypothesis. In this case, they all do. Okay. Next thing I'm going to look for is my null and alternative hypotheses have to be about a parameter, right? Have to be about mu or p or some population thing. And so that eliminates D, right? So this, D is out because I can't talk about X bar. The reason, or not the reason, but kind of a reminder is I know that X bar 1 is not the same as X bar 2. So it's kind of silly to say, oh, do I think that these are different? I can look at them and I know that they're not, or that they are, I guess. Okay, so then in our case, right, we decided on this one. The other two is just greater than or less than. And so we want the two-sided test to test a difference, right? I don't know. Yeah, we can handle a one-sided test, but I think the problem is they made one-sided tests optional in the textbook, but it opens up so many more different types of problems that we could tackle that I like to introduce it and then we know. But it's optional because you can always run a two-sided test and your conclusions are always correct, right? And so, or reasonable, I should say, not correct. Okay, so I'm gonna go with A. Yes. Oh, I didn't read the question, did I? Oh my gosh. 1 carat diamonds is higher than the average point price. She keeps flip-flopping. Scratch this. 1 carat diamond higher than 99. sorry. Thanks for reading the question. I didn't read it. I thought she'd committed, but guess not. Okay. So which one are we testing? Let me just scroll ahead here. How does she find the p-value? I guess we'll find out. Can't tell from there. Fine. We'll be prepared for either alternative hypothesis. In fact, it might be nice to compare the two. This one makes more sense. I'm happy about that. Okay. This one's kind of sneaky, and I'm going to use this list of conditions that do not need to be satisfied to also reiterate the conditions for a means type of question. And so, so it's kind of in a weird way, but now that we have two samples, right? So before, is that the door? See, thank you. I'll get there. But I'm running out of classes to figure it out. When we have two samples, right, then we need to make sure that these two samples are independent of each other, right? Otherwise, it's a matched pairs or a paired data situation, right? If they're not independent of each other. So that's our first thing. So here, the point price of 1.99 carat diamond in the sample should be independent of another, and the point price of 1 carat diamond should be independent of another as well. This is saying that we need independence within the groups, which I skipped to the next one, but. So in the one sample case, we said, okay, all my data points have to be independent of each other. Okay? And that was one of our conditions. One of the ways that I could ensure that is by randomly sampling, right? And then another condition was that if my sample size is less than 30, then I just have to make sure that it's not terribly skewed. Then I can go ahead. If it's greater than 30, we can even handle quite a bit of skew. Okay, so it's a robust statistic. So we still have to have independence within each of the groups, but then because I have two groups, I need to extend it. So the point prices of 0.99 carat and 1 carat diamonds in the sample should be independent, which is between group independence. For the normality condition, as long as the distributions of point prices in the two groups is not extremely skewed, then we can go ahead. Okay. And so here, this is the normality condition. The wrong choice is that both sample sizes should be at least 30. Now, the reason this is wrong is pretty sneaky. So here, like I was saying, we allow for smaller sample sizes, whereas the phrasing of this says that you have to have at least 30. That's not true. We can handle smaller sample sizes as long as the distribution is relatively normal. And even then, we are pretty flexible on that condition. And so we can handle smaller sample sizes as long as we assume, and maybe I'll say we can assume, as we can assume there are no outliers. If it's larger than 30, we can handle some outliers even. right? So for that reason, you can always do a t-test. There are very rare scenarios where you can't do it. So sometimes I even say on the final exam, for example, I'll say, assume the conditions for inference are satisfied. You can go ahead and just assume that. Right. Nice. That's the answer one. We've already looked at the test statistics, so the t, yeah, but I wanted to show you what the proper degrees of freedom calculation is, so that you can be glad that you don't have to do it. You know and recognize all these components. S1 squared over N1 plus S1 squared over N2 squared over 1 divided by N1 minus 1, S1 squared over N1 squared plus 1 over N2 minus 1, S squared. You could do that. Or just take the smaller sample size minus 1. Sold? Nice. So if you use Excel, it'll do this, obviously, because it's a relatively simple thing to program and just redo, right? But for us, we're going to use, right, or just the smaller sample size minus 1.
This formula sheet's making it look like we do the degrees of freedom for both samples. So are we just choosing the smallest one?
So this minimum function,
Yeah.
so let's say, so if I let N1 be 29 and N2 is 25, how the minimum function works is the minimum of 29 minus 1 and 25 minus 1, which is the minimum of 28 or 24. Now the minimum function just picks the smaller one.
Okay.
So it's just a technical way of writing the smaller sample size minus 1. Whether you, so yeah, that one's, yeah, kind of sneaky. I always write it this way because for me, writing it mathematically makes more sense. But if you want to write it in words, right, the smaller sample size is 25. So my degrees of freedom is 25 minus 1, which is 24. That's totally fine, right? But this is a little bit of shorthand for writing that out. Okay, whoops. I'm just going to add a page so we can do this. I feel like in peace without the answer right on the sheet. It's there, but. So we said our null hypothesis was mu 99 is equal to mu 100 or some version of that. Right. As long as you're indicating which group, and you can use 0.99 and 1 if you wanted. And so this is step 1, state the hypotheses. We've already done it like 3 times, so that's why I'm going a little bit faster. But we wanted to show, let's assume that we're doing the one-sided test because we can handle it. Is less than mu 100, right? This tells me that it's a one-sided test. And then as long as we're consistent, that's okay. Step 2 is do the test, which is technically calculate the test statistic. But that's so boring. Or it sounds boring. smush it together. So T is our test statistic, right? Not because T starts with a test or a test starts with T, but because we're following the T distribution, right? And so we've got x1 bar minus x2 bar. Technically, and I'll just put it in little kind of faint marks here, minus mu1 minus mu2, but this is always going to be 0, right? So I don't even write that. Not even on your formula sheet do I write it, so you don't have to write it out. Divided by the square root of s1 squared over n1 plus s2 squared over n2. One of the main things that people forget to do is squaring the standard deviations before you divide by n, or forgetting to take the square root. So there's lots of opportunity to kind of forget to do something. And so I want you to be really careful. Now I'm going to do this calculation in Desmos so that I can copy it out. And let me see if I can do, does it show you both? Okay, great. Because I need to have these values. Okay. S1, as long as you're consistent with your groupings. Notice that I'm sloppy here. I'm not really denoting, it's kind of tiny, which one is group 1 and which one's group 2. I've established it up here, so I'm a little bit lazy and I don't keep going with the subscripts, right? But so you're allowed to do that as well. Okay, so what do I want to do? I want to take S1, which is 13.32 squared, and then I want to divide it by, divide that by N1, which was 23. Close my brackets, right? Just tell it to do these calculations. And I wish I could blow it up, but I can't. Separately, using brackets. S2 was 12.22 squared, then divided by N2, which is 30. Close that bracket. So inside my square root, I get 12.69. Now I'm going to take the square root of the previous answer, and I get 3.5625. Now, on the next line, I'm going to do x1 44.5 minus 53.43 divided by the previous answer to get my t, and that's what I'm going to screenshot and bring in. Because otherwise it's really hard to write out how I did the calculations on my calculator. Oh, I'm gonna crop this up here because I don't need this. There. And scoot it over here. So then I find that, hey, come on. It's not letting me hit my pen. Does not want me to write anything else. T is roughly negative 2.506644499-ish. Let the t-table be your guide as to how many decimal places you need, right? The t-table gives t's to 3 decimal places, and so you're going to want to keep at least 3 decimal places. You can keep more, right? Because all you're trying to do is place it between 2 values. So sometimes it might be nice to keep more, but t is roughly negative 2.507 to 3 decimal places. Telling me that the difference in the means from my sample is 2.5-ish standard errors below 0, right? And so just as using 2 standard errors as my guide, right? Anything beyond 2 standard errors, I feel like I'm maybe gonna reject H naught, right? But let's just confirm. So crazy. Okay, step 3 is find the p-value still. To find the p-value, we need our degrees of freedoms. So I made it plural. Degrees of freedom? Just one, there's only one. The degrees of freedom is the minimum of n1 minus 1 or n2 minus 1. So I just write out what's on your formula sheet, plug in the values, and I am going to write across, otherwise it's too long for what you're doing. So the minimum of, I think, 23, yep, 23 minus 1 or 30 minus 1, which is 22. So then, using the t-table with degrees of freedom equal to 22, which it is a line on the t-table, so we're allowed to use it. Okay. We find okay, what do we find here? We find so I've got 22 degrees of freedom. So I'm going to highlight that row. Weep. And waste some space, I guess, but I'm going to put it on here. We find that, and I'm going to zoom in here. I'm trying to place where my t would fall on this t-table. So taking the absolute value of t, because all of these are positive, because it's symmetric around 0, right? And so so it would be the same on the other side, on the negative side. And so if I'm looking for 2.5, I would be, down to the wire. Okay, let's see here. 2.507, I go back and just confirm which side of 2.508 I would be on. Okay, looks good. I would be on the left-hand side. So I'm somewhere between these two values. Okay. In terms of showing our work, we're going to use the same structure, and it feels tedious in the beginning, but it's explaining everything that you've done, right? So you can say, using the t-table with 22 degrees of freedom, we find that the absolute value of t equal to, so you put your calculated t in the middle, negative 2.507. The absolute value drops the negative, is between two values, is between 2.183 and 2.508. And I link it with a so or therefore or something like that, something snazzy. Then what do? Then I trace down to whether I want, now this is where you need to remind yourself, do I have a one-sided P or a two-sided P, right? So then you go back to your null hypothesis and say, well, this is where it would change, right? If we did that first one that she suggested, the difference in the mean prices, then we would have, this is our two-sided p-value, but we're doing a one-sided test and we'll stick with that. which means that our one-sided p-value is between these two values. Now, it's really important that if you're keeping the inequalities the same, like I like to do, then you have to read these from smallest to largest, right? So from right to left. And it's your job to show off all the things that you know. So why not say one-sided p-value is between 0.01 and 0.02. Okay. I have a range for my p-value. Cool. I can still use that to compare it to 0.05, my alpha level. We weren't given an alpha level, I don't think. Don't remember seeing one. No, thanks. I didn't want to scroll all the way up. But I can still compare something between 0.01 and 0.02. How does it compare to 0.05? It's all less than 0.05, right? And even if we used a two-sided test, it'd be between 0.02 and 0.04. Notice that that is just these two things multiplied by 2, which is what we used to do for the z's, right? So so kind of redundant to have the two-sided p as well as the 1, but or vice versa, I guess. But so now we have our p-value and we're ready for a conclusion here. Add a page. Step 4 is our conclusion. Show off everything that you know, right? So, and we always use the same sentence structure, or I do, and I want you to as well. Since the one-sided p-value, right? Since the one-sided p-value is between 0.01 and 0.02, it is less than our assumed alpha level of 0.05. It is less than our assumed alpha level of 0.05, since it's not given. If it was given, you would compare it to the given one. Which means we have enough evidence to reject H naught. To reject H naught in favor of HA. If you're rejecting H naught, you should probably offer something up, right, in favor of HA. But that's only 2 parts of our conclusion, and we know we have to have 3. Therefore, the final part is actually answering the question, but you're going to take the question and reword it as an answer, right? So this, I will snag the question. So therefore, hey, that worked out nicely. The average point price of 1 carat diamonds is significantly higher than the average point price of 0.99 carat diamonds. Period. And sometimes I like to throw in a significantly higher, because that's what the hypothesis test allows us to say, is that it's significantly higher. You can't say that unless you've done a hypothesis test, right? Nice. So again, 3 parts to the conclusion. Since the p-value is between this and this, You compare it to the alpha level. Then what does that mean in terms of your null hypothesis, right? That part's important because we did our testing assuming H naught was true, right? We compared our difference in sample means to 0, which is assuming that the difference is 0, right? And then we can state our conclusion, which is in terms of the question. Nice. Now they did it nice and slow. We found the correct degrees of freedom was 22. Show the work, p-value. And we said that it was between 0.01 and 0.02, right? Yeah. This is where we determine if she was doing a one-sided or a two-sided test, because if the answer is this, then she was doing a one-sided test. If the answer was, I guess it's not on here, right? So then she must have been doing a one-sided test. It just wasn't clear to me. On a test, I'll make it very clear what to do. Okay. What? Oh, her rounding. And it looks like, okay, let's go back. Sloppy Mine. She's the one who wrote the textbook. She rounded, first off. Ultimately, it's not going to make a difference in terms of your conclusion. And so I get it, but she rounded, and she probably used rounded values as she went. So that's going to make a difference, right? In terms of your test statistic. I kept all the values and I got to here. But on the final exam, when you're answering these, right, try to keep as many decimal places as you can, but as long as you're consistent and you follow through, right? So if you end up here rounding to 3 decimal places, which I've told you to do, and you get negative 2.508, then your circle would be between these two values. So as long as you follow through with that, that's totally fine. So then she circled, and I'll erase this because it's going to be very confusing, but she followed these guys, which still doesn't look right. Let's see here. So then, where is she? She .025. Feel like maybe she's using a more precise t-table. Anyways, do what I did for our hypothesis test that we did together. And I'll go back and erase those that I drew on there. Something tells me she has a bigger table or something. Okay, that's okay. There's lots of different versions of the t-table, but they all do the same thing. And in the end, you can use software. This is our code, but you can use Excel, right? You've seen that in the lab. You know how to find probabilities associated with t's, right, in Excel. So you could do that and find the actual p-value. Okay, so our conclusion, we've already stated our conclusion, but now what we kind of want to think about, and I could be convinced either way, right? How, if at all, would this conclusion change your behavior if you went diamond shopping, all right? And so a couple of options, right? We've established that the point price for a 0.99 carat diamond is significantly less than a 1 carat diamond, right? And so one option would be maybe buy a 0.99 carat diamond, see if you can get away with it. It looks like 1 carat, smells like 1 carat, but it's significantly cheaper. Could use that, right? But as statisticians, it's often not our job. So I'm talking about me, myself. It's not my job to offer solutions, but in business, it is your job to offer solutions, right? So as a statistician, I get to back away and say, yep, there's a significant difference. Enjoy. And then you say, oh, what am I supposed to do with that? So they're cheaper. Okay, cool. What am I supposed to recommend? Which to me is a lot harder, right? Than my job. My job's just calculating it. So you've got the harder job, in my opinion. We can link our confidence intervals with our hypothesis tests, right? And so the confidence interval is always symmetric, right? And for simplicity, let's center it on 0. T is centered on 0, for example. Z is centered on 0. So if I want to force the alpha level to be 0.05, that's going to be the same as saying, okay, I've got some cutoff where the tail area is less than 0.05. Now we're told that this is a one-sided test, which means I can force the tail area for one of the sides to be 0.05. Okay. And maybe for simplicity, let's force this area to be 0.05, right? This here. But a confidence interval has to be symmetric, right? And so what that means is that I would need to have 0.05 on this tail as well, right? By symmetry. So if I've got 5% in one tail, 5% in the other tail, I've lobbed off 10% total, which means that this is going to be a 90% confidence interval because 90% is what's left in the middle, right? And so here I've got Z star, negative Z star, and positive Z star, which is the critical value in your, let's do T's instead, sorry. It's the same. The critical value in your confidence interval, right? And so what this is emphasizing is that, yes, you can use a confidence interval instead of calculating the test statistic and finding the p-value, because then what you can do is you can take your confidence interval, and if your hypothesized value is inside that interval, you don't have enough evidence to reject H0. It's one of the kind of plausible values, but you can only do that for a two-sided test, right? Or you could alter your confidence interval to match whatever your one-sided hypothesis alpha would be. Okay. So here, notice confidence intervals only correspond to two-sided tests, hypothesis tests. So we landed on 90%. Okay. Forgot she had that image. So for finding our critical value, if we want to make a confidence interval, then the critical value for a confidence interval for the average difference between the point prices of 0.99 and 1 carat diamonds, this is shaping up to be a confidence interval type of question. Yeah. And so we know, recall that the degrees of freedom was 22. we'll need that because our T star relies on 22 degrees of freedom. What confidence interval do we want? Let me check. 1.72, making me think it's for a 90% confidence interval, but let me confirm. Oh, you know what? You know what? Fine. No cutting corners, Emily. Copy. Now we come at it from the top. Paste. And so how did I determine which one she did? Well, it wasn't 2, making me think it's not a 95% confidence interval. Notice that for all these 95s, as soon as you hit a reasonably large sample size, it's going to be hovering around 2, right? Kind of closing in on 1.96 as your sample size becomes the population size, right? And so that's how I knew it probably wasn't going to be a 95% confidence interval. And we had just talked about a 90% confidence interval. So I feel like that's where I got that from. So she is using a different table than we are with only 2 decimal places, but that's okay. Because we found 1.717 at 22 degrees of freedom. Let's see what you got. Yeah. Could use software, of course, right? What was it? Inverse something usually. But let's find this confidence interval. I'm going to reword the question in a way as I would word it, right? And so I'm going to say the question for us is construct a 90% confidence interval for the average difference between point prices or the point prices, I guess, the point prices of 0.99 carat and 1 carat diamonds. Gonna add a page here. And you know what? Oh, I wish I'd had those lines when I wrote that. Hey. So just to reiterate how we would state the T star, right? Using the T table, or maybe I'll say, yeah, that's usually how I phrase it. The T table with degrees of freedom equal to 22. I've already shown the work. If you haven't shown the work earlier, you should show it, right? But I'm not going to do things twice. Using the T table with degrees of freedom equal to 22, T star is 1.717. Okay. Then x1 bar minus x2 bar plus minus T star times the standard deviation of group 1 squared over n1 plus the standard deviation of group 2 over n2 Okay. I'm going to maybe cheat a little bit and use Desmos again because I've already calculated the standard error, right? I've already calculated this earlier. So this is from before. From earlier. Once you have it, it's nice to store it in your calculator somewhere just in case you need it. Yeah. And so what I'm going to do is I'm going to call this SC is equal to this. And I hope that that works. Divided by SE. What doesn't like it? I thought you could call stuff. Fine. I've done that before though. Oh. Did not want to do that again. But I did want to have my point estimate conveniently popped up, I guess. And then I want to do, you know what, I'm going to do the lower part first. Even though it shows up as plus minus, I want to remind myself that I have to write it from smallest to largest. So I'm going to go minus. And can I copy this? Minus. Fine, 12.69 163072. So I get, I'll copy it in, but and then 44.5 minus 53.4 plus the root of 12.69163072. Gonna copy that. May as well keep all that. Why not? So then my interval is going to be between negative 12.46 whatever and negative 5.337 blah blah blah. Okay, so let's write down that interval. Oh, my iPad's not happy today. The interval round brackets between negative 12.46 to 5315 and negative 5.3374684996. These is the difference in point prices. So as soon as it's money, I can go ahead and I can round to 2 decimal places. So if you wanted to skip there, that's totally fine. So then between negative $12.46 up to negative $5.34. That's the difference in the mean point prices. Yeah. So in terms of our interpretation, we say, and I guess I'm not quite ready for that yet, for copying and stealing it. Hey. It's letting me pick all the options except for the pen. We are 90% because we built a 90% confidence interval, 90% confident. This is the exact same blurb that we've been using and probably memorizing, hopefully memorizing, right? That the interval from negative $12.46 to negative $5.34. Oh, nope. Oh my gosh. Can't see what's going on here. Just wanted to erase this, but instead, okay, there. Hey, there's a rogue comma there. To negative 534 captures. And then that's when we introduce the part from the question as our answer, captures the average difference. And I'm just going to steal this because I can. Captures the average difference. Oh, I overcommitted. The average difference. I'll get there. Between the point prices of 0.99 carat and 1 carat diamonds. So the average difference between these two things, right, is going to sound very similar to the mean difference, right? So the average difference between these two things, right? Whereas if I'm talking about the mean of the differences, it's going to sound very, very similar, right? What does that mean? We did 0.99 carat diamonds minus 1 carat diamonds. So that means that on average, right, 1 carat diamonds are between $5.34 and $12.46 higher per point. That's not an extension that I expect out of you, but that's where it would go, right? And so here, therefore, 1 carat is on average 534 to 1246. Now it's a confidence interval, so we're 90% confident that 1 carat diamonds on average are between 5.34 to $12.46 more expensive per point. Remember, a 1 carat diamond has 100 points, so kind of equates to something, right, per point, then 0.99 carat diamonds. Right. Nice. Let's see if there's anything. So we did this, and that's it. Whew. I
not multiply the t-value on your.
I didn't.
Yeah.
Oh, and now you tell me.
Okay, is that why it was different?
What did I do? I'll do it in red to really punish myself. T-star. I'll fix it, but you don't have to be here for that. It's going to change everything. It's going to change the interval. It's going to change, but our interpretation is the same, just different numbers. Oh my gosh. And nobody called me out on it.
I think I started doing that.
You're like, oh, she screwed up. Oh, well, that's okay. Thank you. Thank you. I'll fix it before I post the notes. So just as a side note, so we're not doing, so this is 7.4. It's the extension, right? So before we did chi-squared for multiple proportions, more than 2. An ANOVA is the extension where you have more than 2 sample means and you want to compare them. So I made a bonus assignment. If you want to flip through the slides or flip through the textbook, you can do the bonus assignment. If not, that's okay. I'm just gonna leave it as optional. And that means I don't see you until Monday for some regression, but I am assuming that you've done the lab, at least lab 9, before Monday. Okay. That's a curveball. And rude, right? I know,
Is there a lab today?
if you want.
Oh.
Yeah. I'll stop this recording. I